Okay, welcome to Monday, Lab 9, right? Or is it Lab 8? Lab 9. Okay. I'm losing track of time already. Okay, so this week, I'm thinking we'll go through the skeleton code first for each of the problems, and then depending on if there's time, which there probably will be, then we can do like one of the trickier ones. Okay, let's screen share. MATLAB. Okay. Let's see. Did I? Yep. Okay. Whoops. I'm gonna navigate to the correct folder. Give me a sec. And there we go. And some of these functions you see on the left, by the way, are from a deleted problem that was too hard to give out. Cubic polydiff, polydiff without the M. There we go. Okay, let's go through these in order. So there's two problems that are in Lab 9. There's one that has you calculate the differentiate a cubic, like x to the power of 3 plus x to the power of 2 plus x to the power of 1 plus x, plus 1. There's one that asks you to do something of any order, not just a cubic, not just an order of 3, but any amount. This could be like x to the power of 10,093 or something. And then finally, you're going to do one that can repeat the polydiff, the differentiation, m number of times. So it needs to work with any number of any order polynomial and differentiate it any number of times. So it's a scaffolded problem. Part 1, Part 2, and Part 3. So just an overview of the skeleton code of how the LXF solutions want you to do it. I mean, this can be done in 2 lines. This one is pretty simple. Before I go into it, though, I kind of want to do a conceptual overview of what exactly we're trying to do here. Okay, let's start with, let's do an easy one. X to the power of 3 plus 2x to the power of 2 plus x. Now let's do 3x plus 4. Okay, we're going to turn this into 3x squared. Let's write it so that it's all lined up and nice. 3x to the power of 2 plus 4x plus 3. So the way we're going to do this using MATLAB, right, is we're going to turn each of these, I'll label this 1, label this 2, each into a vector. I want something in the form of ax equals b. Or in other words, I want this to be my 1 and this to be my 2. B is like the output. It's once we transform x using the matrix A, we'll get B. In other words, A is like the differentiation matrix, diff matrix. Okay, what's that going to look like? Well, let's look at what we have here. We have our x. This is just an example x. 1, 2, 3, 4. And that's going to turn it into, by the way, this is going to be, like this is the x to the power of 3, x to the power of 2, x to the power of 1, x to the power of 0. That's what this means. These are like the coefficients. And this is going to turn it into something like, let's see. Well, there's going to be no x to the power of 3, so this is going to be 0. This is going to be 3, this is going to be 4, and that's going to be 3. See what I did here? I've turned the coefficients of these into the elements of each of these vectors. So this is like y. Now, how do I want to write this? I'll write it f prime of x. The coefficients, to be specific, the coefficients of f prime x. And then this is our f of x. Polynomial transformed by some 4x4 matrix returns this differential, the derivative of that polynomial. So the question is, how do we assemble this like differentiation matrix? Like that's this first part over here. I'll call this like 3, step 3. All right. Let's look at. Let me clear this in 3, 2, 1. Let's look at these each individually. So let's say that we have like x to the power of 3, and then that gets turned into. I'm going to call this. Before I do this, I'm going to write this in the way they want to do it. It's a little different, but it's going to be. We're going to flip this around, and we're going to write it like a naught, the constant first, and then we're going to like go up in order. A2x squared plus a3 x to the power of 3. So how do these change? Well, let's look at each of these terms individually. Let's start with the hold on a second. I have like a naught, a1, a2, and a3. And I want this to become my new a naught, like our new constants, basically. So let me check what that's going to look like. Okay, I got it. This is going to be. I'll just call these prime. I mean, this is always going to be 0 down here because of the nature of differentiation. Let's do this, and this is going to be this. I'm going to write these as like 1 x to the power of 1, x to the power of 2, x to the power of 3. So let's look at these individually. I'm going to start with the a3 x to the power of 3. So once we differentiate this, like this is going to give us our new x to the power of 2 term. Like we can kind of draw an arrow that kind of points from, I'll draw it in blue, from here to here. Once we do this, whatever this is going to be 3. We'll bring down the 3 because of the power rule, and then it's going to be whatever this a3 is. So 3 times a3. Well, that's going to be our a2 prime. That's going to be like our new x to the power of 2 coefficient. So this is like a2 prime. And we can continue this process, like drawing these arrows down to this one. You can see like this one actually doesn't matter. And then we'll say that like a2 times a2 is equal to our a1 prime. So the way we construct this differential matrix is like this. I want to take all of these coefficients, a0, a1, a2, a3, and I want to use those to find whatever is in this end, like this exact element of that row. Now let me demonstrate to see what I show you what I mean by that. How do I know this last one's 0, right? That's like saying like the x to the power of 3 term in our derivative is 0. So I'm going to take 0 of a0, 0 of a1, 0 of a2, and 0 of a3. And that's the final row. I'm going to take nothing of these, and then I'm going to have that be my bottom element of that differentiation. What about the third row? Well, we're going to want. Well, how do we say we're going to get our a2 prime? Okay, I'm gonna ask you guys. I know the answer, but I want to see if you guys can understand like what's going on here. How many of a0, a1, a2, a3 do I need to get this a2 prime? These are my ingredients. This is what I'm trying to bake. How do I make my a2 prime? Can anyone tell me?
You just need a3.
A3. So
7,
then
2.
there's going to be something here. How many of
3.
A3 do I need?
3.
3. So this one's going to be 3. Okay, let me check the chat. (2A2) is going to be a little bit later. So for now, though, do we need anything else? A0, A1, A2 to get this A2 prime. Is there anything else in this row?
No, they're just zeros.
Right. The pattern you'll see, and well, let's do this next row and I'll kind of show you. So 2A2, we're getting our 2A2 for this A1 prime, right? We're saying like A1 prime is equal to 2A2. Because by the power rule, like 2A2x to the power of 2 this becomes 2A2x, and that's the derivative. So this is our like f of x. If this is our f of x, then this becomes our f prime of x. So to get this, which is like 1x squared x to the power of 3, to get this x term of the derivative, we need to look at the x squared term of the original function. So this is 2. We're just going to take 2 of A2. And the rest of these are 0. And then this one, I think you can follow the pattern, is just 1. You'll take 1 of A1, and that's going to be your constant term of your derivative. Notice a pattern here. This is always going to follow the order of the order 1, 2, 3 because it's a cubic, and it's going to continue onward if we go to a higher order polynomial, this is going to be a bigger matrix, and it's going to have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we can kind of imagine it like stretching out, like here's 4, here's 5, ... That's the pattern we're looking at here. So this, if we zoom out a little bit, this is just a conceptual way of how we do a matrix representation of differentiation. It's a machine that turns a vector that is a polynomial into another polynomial, which is its derivative. It seems a bit like convoluted the way we're doing this, but it's a way of automating this process into our code, which is going to be useful once we get into our like other higher order functions. Okay, any questions so far before I erase this? Clearing in 3, 2, 1. So I kind of just show you how to do the differentiation matrix. And then solving for df, I mean, we can go over this later if people want. But I mean, I think this one is pretty straightforward. I'm going to polydiff now. Now, for reasons that you can probably guess, this is going to depend on what degree your polynomial is. The differentiation matrix. So before we had like a 1, 2, 3, but for this one, you're going to want to continue down this way, and then you're going to have a bigger matrix where this is going to be, it's going to be like an n plus 1, n plus 1 by n plus 1 matrix. If you're like let's say you're order 5, right? You're going to have like x0 plus x1. No, let's use A. Hold on, let me make this proper A's. A0 plus A1x ... all the way up to A5x to the power of 5. So there's going to be like 6 of these coefficients that we'll need to worry about. So this will be all the way down to, it'll be a 6 by 6 matrix, just for example. And you'll want to be able to code this matrix based on the degree of the polynomial. Clearing in 3, 2, 1. Not much more to say about this one. I mean, you're going to have your n. You're going to have the order of the polynomial. You're going to have the differentiation matrix. The way they do it is they do this multiple times. There's probably like a way to do it using like looping, but the way they do it is they not want to spoil the answer, but they just do it m times, and it's just like a matter of like matrix multiplication. And I think you can use like,
I would probably just construct. Can you use the reshape function for this? Like construct a vector from 1 till the degree of the polynomial -1 and reshape it into a square matrix? Probably not, right?
Wait, why would you need to reshape it? I'm confused.
Oh, because we don't want a vector from 1 to, let's say, 5. We want a matrix that has that diagonal.
Oh, I see.
So I was thinking of reshaping something into a diagonal matrix that only has 1 through your target number on the main diagonal, and then add a row of zeros at the start and sorry, a column of zeros at the start and a row of zeros.
Vector with n components that square matrix. I think this should, hold on. I want to try something. 1, 2, 3. Okay, you can do that. You can use the diag function.
That's exactly what you need for this. And then you add zeros at the start and at the end, or you create a matrix full of zeros of the precise that you need the final matrix, and you make the elements rows 1 through n minus 1 and 2 through and columns 2 through n to be equal to this diagonal.
Yep. Okay, I think once we do that, the rest kind of falls into place. Here is problem 2. Stop me if there's any questions. So linear regression, just a quick review. We have some number of points, and we want to draw a line through it. And for this one, I think there's a couple different ways of doing like linear regression. This is the line y equals ax. And you'll notice that sometimes we'll have this like plus b over here. The reason we don't have this plus b for the moment means that whatever line we draw means we have to shoot the line from the origin all the way up here. We're standing at the origin. If we have the plus b, that means we can stand wherever we want. We can do like here and then shoot the lines through here. We can do this, we can do this. But since we have a specific model that says, hey, this is just going to be y equals a plus y a times x, and we're like setting b equal to 0, that means that we're shooting it specifically from the origin. That's what that means. So no line is going to cross through every single point. It's not possible. But we can get our best guess, and that's why we want to do this process. So we'll be given an x and a y. Like this is like x1, y1, like this point right here. X2, y2. You get the idea. So these will be vectors. Here's your x. Here is our y. And then, so because of the nature of these points, like there's not going to be any like matrix that gives us a, like there's no way to like write into a typical like, because the way we're doing this, because these points are not collinear with each other, This is like they call it an overdetermined system. Like we have too many constraints. Like, oh, you have to pass through this point, and you have to pass through this point. Okay, I can do that. But you also have to pass through this point. Okay, well, like that's not possible because they're not collinear. So we need to have a different strategy. So I'm not gonna spoil what exactly they're doing here unless I'll do that after the skeleton code. But like here's basically what we want to do. Find the coefficients, and in this case, there's only one coefficient. That's going to be our a, and we're trying to make sure that we're minimizing a certain quantity called the root mean square error. And let me kind of get rid of this so I have space to write. Root mean square error. You may have seen this before. If not, the idea is you want to minimize the sum of the squares of the residuals. What that means is this. Here's the line, here's a point, and this right here is called the residual. It's like the error. That's another way to call it. And there's a few things we want to do. Here's the y. Let's see. This is our y hat. This is our guess. Here's what we're doing with this. Okay, so step 1, y minus y hat. That's the error. Step 2, y minus y the hat squared. What this does is it gets rid of any signs. Like it's possible if we were going to add all these up, then we'd have like pluses and minuses, and then like we wouldn't really be minimizing the error. We'd be minimizing like the absolute. Like if we have like here's an error and then here's an error, right? And then they're both the same residual. Like this is +1, this is -1. Then we add them all up and we get an error of 0. That's pretty good, right? Well, the problem is like it's 1 this way and then -1 this way. So that's not that good. So we want this to be error squared to eliminate any sort of signs. Now, to add them all up, we just do, I'll write the sigma, sum of y hat, well, y minus y hat squared. Notice that the order of these doesn't matter because we're squaring it. And then we'll divide that all by m. Like how many of these, like the number of points. And that's going to be the root mean square error. See something in the chat? Okay. If root mean, I'm getting a private message. If the root mean squared error is a sum, why don't we use summation or a for loop? We can, but there's a way to do it without actually doing that. Because the thing is your y and your y hat are both vectors. So there is a way to add up like if we have like y minus y hat, like this is like a vector of some sorts. So there is a way to add up, I'll tell it to you, it's sum, to just add up all of the elements of that vector. You can do a for loop. You're allowed to do that. But I don't think it is necessary. Okay, clearing this in 3, 2, 1. Okay, pause for any questions. I assume this is the one that people are going to have questions about. It's a little bit more complicated. It's complicated because there's multiple different functions we're working with. We're not going to be working with a linear model. We're going to be working with 3 different ones. We're going to have like 3 different coefficients. Y equals, and this is our model, linear model, equals a times some function plus b times some function plus c. Here is our coefficients. We're going to want to end up with a comma b comma c. And what's this model number we're working with? Index of the, so it's whichever model is the best. That's what this means. So we're going to want to generate, the way they do it is they have something like a matrix of coefficients, like 1, 2, 3, A, B, C. It's like the Michael Jackson song. no, not no, Jackson 5 saw, sorry. You have like A1, A2, A3. Like there's like an A, B, C for each single model, and this coefficient matrix stores that. And I mean, I guess it's not too complicated if no, it's deceptively easy. They give you the functions up here, and then all you need to do is compute what your predicted, like your y hat is, and then like you already know what the root mean square error is. It's complicated. It's complicated, but not. It's just the same thing every single time. Simply y hat minus y, square it, and then add them all up, and then square root that. Oh yeah, I forgot to mention. Yeah. I mean, the steps of calculating the root mean square error kind of are in the name, right? There's the square root of the mean of squared error. That's all it is. That's basically all it is. Okay, there was more, but it was deleted from the lab. So clearance in 3, 2, 1. There was a problem 3 that was removed, but simply focus on the ones that are here. Problem 1, problem 2. I believe this is the end of, yeah. Okay, we got that done for like 40 minutes. These are scaffolded problems. They kind of build on each other. So yeah, attempt them in order. I mean, like the parts in order, like 1.1, 1.2, 1.3, and then like just within the same problem. Linear regression before doing my best regression. Okay. I'm thinking about, what do you think is the trickiest? What do people want me to go over? I can go through like 50% of it, kind of show the entire thing. Take your pick.
Should we poll? Or...
My best regression. Actually, Jose, do you think it's best to like skip to like the most complex ones, or like, because if I feel that people should understand how to do like the first two before we like the first parts before we like attempt these ones, like these ones before these.
I agree. Yeah, I don't really think it will be beneficial to jump into the most complicated version of everything without going over the basics.
Mhm.
So yeah, I think we should go step by step rather than jump into the last version.
Sure. Looking at these, I think like if you understand this part, like you've already understood half of this problem, and I think that's, yeah. Unless the professor one day says like, go ahead and show all the solutions, but I think it's instructive to let just go in order. So yeah, let's just do that then.
What about this? What if we try to cover so are both problems 3 parts? Let me check. The polydiff is 3 parts, and
yes, a 3-parter for problem 1, and then a 2-parter for the second one.
Because I was gonna suggest going over the most basic one, part 1.1 today, and maybe answer questions of 1.3 on Wednesday, and do something similar for problem 2. But
we have time to do all of that today, I feel.
Yeah, probably.
Okay. let's see this. How are we going to create our differentiation matrix? Does someone remember how we do that? I mean, I guess it's kind of hard to say that probably. Okay, well let's break it down. We have like a few parts to it, I guess. So then here. We want this to be like 1, 2, 3, and then the rest of these are going to be zeros. So this, okay, how do we create this inside part? I guess we're going to want to have first the vector 1, 2, 3. And then to create the diagonal, we're going to want diagonal of 1, 2, 3. Now, if we want, hang on a second. Let me take a look at something real quick. I think there's a cleaner way to do this than padding it with a bunch of zeros. Okay, so diagonal matrices, the kth diagonal. K greater than 0 is above the main diagonal. Let me try something. Let's do 1, 2, 3, comma 1. That's going to be the first diagonal. And I'm going to see if this works. Oh, let's do that then.
That's fantastic. Also, just as a small comment for all of you guys, whenever you're trying a new function, this is the way to do it. Just put random inputs to which you know what to expect, what answer to expect. Just put them into the command window and test with the variables until you know how to use the function.
Yeah. If you wanted it to be -1, this is what would happen. I guarantee you half of the questions we get in office hours, DMs, not that I'm asking you guys to stop sending those, keep them coming, but you can test them out in some capacity within MATLAB, like we've done here. I don't know everything about MATLAB, but I know how to some extent.
Find out.
Yeah, it's a lot of figuring out. Okay, DF. Well, what do they want for DF? Okay, okay. Someone tell me what we're gonna put here. It's gonna involve cubic D. A freebie. It was very lonely last week with no one asking questions because they sent out the solutions. Cubic DF. Yeah, coefficient. Coefficient, yeah, you multiply, you transform F into F prime, yeah. And then, have I set this up properly? Let's go to the correct one. Yeah, okay, this is the correct one. Okay, let's test it out. Someone give me a 4-element vector. I'm going to type in cubic polydiff. Cubic. Can someone give me 4 numbers?
Ideally integers. 4, 5, 2, 3.
4. Let's see. F is. Wait a second.
Be a vector. So.
Was this a vector or is it a?
It's a vector. Look at line 4.
Okay. So then that's going to be, okay, it's a column vector. Sorry, spacing out for a moment. 4, 3, 2, 3. Oh, I see, yeah. Does that look right? 5, so 5x, 2x squared. Okay, 5x becomes 5, 2x squared becomes 4x, 3x to the power of 3 becomes 9x to the power of 2. That's correct. 4x, 9x to the power of 2. And Okay. Look good to me. Clearing.
Remember
Dry.
that the original polynomial here meant 3x cubed plus 2x squared plus 5x plus 4. So this should be the derivative.
X squared. That goes with the 9. Yeah, checks out. Okay, let's keep going. Let's try something harder. So I think so I know we usually we'll do something a little different. We'll leave the poly diff m and then the best regression to your guys' devices. We'll make you think a little bit, but this should provide a pretty good scaffolding for it. It kind of defeats the purpose and if we like skip to the end. Okay. Degree of the polynomial. Someone tell me how we do this. Can someone? It's one line. It'll be something like this. We can use the same f. Degree of the polynomial. If we're given like, here, I'm gonna take this. Okay, I'm gonna write f equals
suggestion by Ali is length of f.
Length of f. Sounds good to me.
It's a pretty good guess.
6. Oh, no, let's add pi. I like pi. Length of f. Looks good to me.
Does it
wait,
work actually though?
Wait, hold on. Length of the polynomial. Wait, this is not the degree of the polynomial. No, this is not. Right?
There's a little caveat to the degree of the polynomial. It's not just the length of f. Remember that one of the elements of f is just the constant element. So if we have 3x squared plus 2x plus 1, we have 3 coefficients in there, but it's a degree 2 polynomial. So we don't count the constant element. We should subtract 1. Exactly. There's a suggestion to subtract 1.
Yep. Okay, differentiation matrix. We can reference this one. Let's copy this over and see what we need to change. Differentiation matrix. We create 1, 2, 3 along the diagonals. This diagonal I don't think changes. We leave that as 1, but this one does need to. So it'll be like 1, 2, 3 ... But how are we going to do that? Let's try and do this without a for loop, by the way. Can someone tell me how we make this vector over here?
Just as a side note, I usually like avoiding for loops in my codes because they take time. And when you run something 10 million times, it adds up. It's not necessary for this exercise, which is a lot smaller, but just for your consideration in future projects. There's a suggestion 1 through the final element of f.
So it'll be like, for example, if we had like 4, 5, 9 like that?
No, the vector, the first suggestion was 1, so if you look at the chart, 1 through f end.
1 through f.
The problem with doing that is that f end is the last coefficient of the polynomial. So if we look at the example that Dennis has here for a degree 4 polynomial, f end is 3.14 pi. So we would try to create a vector from 1 through pi, which first of all, the computer wouldn't know how to go 1, 2, 3, and then what does it do? Actually, I think it would stop at 3. I'm not sure what it would do, but it's not exactly what we want.
It would
if
stop
that's coefficient 5, it would go up to 5. So the second suggestion works actually better, 1 through n, the degree of the polynomial. And yep, that's exactly what we want.
1 to n. And we'll test this out to make sure that it works in case we make any semicolons. Now let's take out the semicolons because we want to see exactly what they're doing. Okay, df, that's the same thing, d times f. I don't think I'm spoiling anything by saying that. All right, clearing in 3, 2, and 1. Let's test it out. We have our f as this one. It's like a 4-degree polynomial. Let's see here. Df comma d is going to be the result of polydiff f. Okay, differentiation matrix
looks good.
Yeah, it looks good to me. Yeah. And this is like pi times 4 or something.
Yeah.
And let's try one more. Let's do polydiff. How do we do this? It's a column vector, so let's do f appended with f. So this will be a 9-degree polynomial with 1 through 9 along the diagonal, the first diagonal, and these should be pretty large. Okay, looks good to me. So polydiff m, I'll leave to your own devices. I'll leave the season finale for you guys to watch. All right, linear regression. Coefficients with a backslash operator. Okay, we're given an x, we're given a y. How are we going to do this, I wonder? Well, we have a linear model over here. So we're trying to find what A is. Am I setting this up right? Hold on. Like, let's say we have like 3 points. No, wait, hold on. This is just one. It's going to be A times, well, it's going to be some A. And we're going to want this to be y1, y2, and y3. And this is like y hat. So hat means guess.
Or prediction, I would call it prediction.
Prediction, thank you. Yeah, it's an educated guess. It's not just BOGO sorting your way to victory. Let's make the hats nice and pretty. So if we are given an x1, I predict that y hat is going to be somewhere around here. It's not going to be exact. Maybe it's somewhere up here or something like that. But I'm going to draw a line up to here. X2, I mean, just continue the trend. I predict the point's going to be right here. Maybe the point's down here, etc. So that's how we're going to get our line. This is going to be like y equals ax. So finding the coefficients. So this is kind of like our matrix in a sense. Well, I mean, let's see. The dimensions are wrong, right?
It's sorry.
Yeah, you're right. This should be like a. This should be transposed. This should be a x1. Thank you. X2, x3 equals y1, y2, y3. Yeah, then the dimension makes sense. It's like 1 by 1 times 1 by 3. And then like dominoes, these match up.
I think the other way also works because a in this case is a scalar, so it doesn't really care. Like it works either way.
No, the other way doesn't work, I think, because you're doing a 1 by 1 times a 3 by 1.
Yeah. But when it's 1 by 1, MATLAB will just take it as a scalar multiplication rather than a matrix multiplication.
Let's try it out. Just this. No, okay, no, you're right. Yeah. What am I saying?
As a general case for higher dimensions, then absolutely you do need to make this check for dimensionality. But in this case, a row vector or column vector either works, as long as both are the same type of vector.
So
Either
if we're
both
trying
column
to,
or both row.
okay,
Sorry,
we're trying to solve. Sorry. I think if we're trying to fit the form that we usually go with, we can kind of think of this as like the A, X, and then B. Where like this is our X, and this is our A, and this is our B. So to find our X, as you may have seen before, it's like A / B. So in this case, it would be A equals our X / Y. So that's going to be, I'm not used to using the back, like finding the / in my, like this is the only time I ever use that. Okay.
The only time you ever done what?
The only time I've like ever used the / key on my keyboard.
Oh,
not like the first time. I mean, like this is the only like scenario.
yeah. Same for me. Does the / work with two vector inputs though? I'm not sure it does. I think it.
Let's try it. If you're not sure, if we're not sure what it. X equals 1, 2, 3. Y equals 4, 5, 6. This is probably going to return. These are probably like collinear, I think.
And it should return 2.
X.
Oh no, not 2. Not 2. What I'm saying. What am I saying?
Oh, hold on. Should it be Y / X? Hold on a second.
Then probably we should disregard my previous comment.
Okay, that looks better.
Okay.
What's up?
Okay. Yeah. You were right. Because of how MATLAB treats the / operator, then you do care about the direction of the vectors.
Okay, so these need to be column vectors then. Okay. Can set of points. I think they'll give it to us like that. Let me just make sure of that. 2.1 linear regression column vector. Okay, so this works. This works. And this is not going to be a, like, it's not. Let's try this out. If we use like a linear model, like let's say this is 1, 2, 3, 1, 2, 3, 4, 5, 6. Put a point right here, put a point right here, put a point right here. If this would be a line, they're collinear, but they're not going to be, we're not going to be able to fit a line to this using our Y equals A times X, because remember, we can't stand here. We have to stand over here. We have to shoot our arrow up from the origin, not from like the point where this like line of points, this Orion's belt, hits the Y-axis. Instead, we'll need to draw a best fit line, and like that's going to be the slope that minimizes that.
You could plot these things out of your own curiosity if you want to see it graphically.
Mm-hmm. Okay, and this is actually not going to pass through this entire exact point. It's going to probably going to be like, what is that? 2.2857. I don't know where it's going to pass through, but okay. But that's just an example. So Y hat, I mean, this part should be pretty straightforward. What's Y hat? Can someone tell me? It's going to involve our X. What do we need to do to our X to get our prediction? Wait, is someone saying something right now? I can't hear.
There's an a times x suggestion, and yep, that's exactly it. We have our coefficients already, and we have our data. Our data is x, and we just apply the linear function a times x.
And note that it doesn't give us exactly y. It can give us exactly y if this is like an exactly fitting line. But since it's a line of best fit, then we're going to, this is the best we can do. This is our prediction. And root mean squared error. I mean, that's just this thing up here. Sum of, we have our y hat, we have our y, we square it. That's this s right here. We sum that up, and then we divide by the total number of, hold on a second. So it's sum divided by the total number, and then we find the square root of that. Is it me, or is this missing a square root?
Let me see. It should be. Yes, it should be the square root of the sum, I think.
Yeah, this should be all this square rooted. Huh, that's weird. They omit this. I'll need to show the solutions later to make sure that they have the same thing, but I believe this square root.
I don't remember if you square. I think you square the sum of the squares, and
if you
then divide by m.
Isn't it? It goes root, mean, squared, error in that order. Let me check that. I'm pretty sure the root is on the outside.
Yeah, you might be right, but usually the error is measured as a norm, and you're probably right. This must be a way to regularize this.
Okay, I see it now. Yeah, it's the square roots of the entire thing.
Yeah, you're absolutely right. I just googled that.
That's one of the things I like about like the root mean squared. It's very, it's unlike a lot of things in engineering. It says what it's actually doing. Root, mean, squared, error. Okay, that's we're done, right? No, wait, we still need to check. Linear regression. X comma y. What's x? What's y? And before I forget, a comma RMSE equals. Oh wait, what? Oh, okay. I needed to. Here, let me do one thing. X equals x prime. Gotta make this a column vector. 4, 5, 6. Now we'll do it. Okay. I realize this is blocking, so here's our a. Here's our root mean squared error. Let's do one more thing. Let's do plot x comma a times x, and we'll need to untrans. I think this is no. I think this works. So this is our line of best fit.
You're only sharing the main MATLAB window, though.
Whoops. Let's. Let me just share my screen.
And just for illustrative purposes, you might want to scatter the original x and y just to show the actual difference between what we were predicting and what we were trying to match.
Whoops. And this goes down to 0, I'm pretty sure. And put this here. Okay. That's my linear regression. That's so we covered 1.1, 1.2, and 2.1. And then polydiff, aka 1.3, and my best regression, aka 2.2, should be we'll leave to you to figure out. Ask questions about that. We basically given you half of this already. My best regression, half of my best regression, and half of my poly. You'll probably know how to do this, and then this is probably the only thing that's different, the differentiation matrix m times. But look up like matrix. I think you should. No, I'll give you one more piece of the puzzle. I think, let's see. Matrix equals magic 3. I believe that what I'm about to do works. Matrix divided to the power of 3. Yeah, it works. Okay. What I did there is I did matrix times matrix times matrix. Matrix rules and like it's the same. It's the same for scalars. It's the same for matrices. Like you can do that. So yeah, that's probably the last piece you'll need for that. Okay.
Someone wants to go through the skeleton of my best regression again.
Oh, I didn't go through. Oh, the skeleton code. Okay, I can do that.
Yeah.
Okay. For the cosine and sine functions. Well, maybe we should do a little bit more skeleton code for this. Let's expand this and we can draw. Yeah, let's do one of them, I think. Here's our y. Okay, we'll do something similar to my best regression. Let's do it simple. y1, y2 is equal to, let's set this up like this first. A f1 plus b f2. Well, we're doing the first one, I guess. I'll illustrate this out as this. A sine of x plus b cosine of x plus c. And this is gonna be like x1. So then this is like something similar, except with x2 and x2. For y hat, we're going to want to have. Let's see how they do this. Let's figure it out. Okay, for this one, we have some function, and it's not going to be linear. So because for this one, the my linear regression, we have we can do this, right? We can write it. You'll notice that we can't just take out an x1 and an x2 into the out of this and make it like an a. We can't write it like this because it's not a linear. It's not a linear system of equations. We have x trapped in this little sign over here. We can't pull it out.
So you would probably want to transform
my mistake.
X data.
Oh, I made a mistake. The A, B, and C are what we want to take out, I believe. Those are the unknowns that we're trying to find.
Yeah.
Okay. Whoops. Yeah. Okay. Never mind. We can use matrices. Okay. Crisis averted. So what are you saying, Jose?
I was just gonna say that you can transform it into a problem that looks like AX equals B by doing exactly what you're doing right now.
2 cosine of x2 and 1. Notice the 1. I need that because I want to multiply c into here. I can't have it as 0. Otherwise, that'll be 0 times c. A, B, C. Just like that. And that becomes my y. y1 and y2. Okay, so y hat. How do I do? Well, let's actually use this form. Okay. Here's our A, here's your X, here's your B. We can do simple A / B here. But we'll first want to construct this. So first of all, what do we want to do? I'm going to rewrite this. Sorry, let me get rid of this in 3, 2, 1. I'm going to write this as such. Y, this is a vector, equals sine of x plus cosine, no, not plus, what am I doing? Cosine of, this is a vector, or kind of a matrix / vector. It is a matrix. Cosine of x And remember, x is a vector, so we can take, before I do anything dumb, let's make sure that we can do this. Sine of 1 up 2. Yes, yes, we can. We totally can. And this is 1. Annotate. Come on, annotate. 1. And let's squeeze in like an A, B, C here. So once we do this, all we need to do is sine of our x plus cosine of x. No, I did it again. Cosine of x, 1. Make this a vector. And this is like our A. We want to find A, B, and C. Hang on.
I'm not sure that I would rather give a name to the transformed X matrix. So let me pull out the annotation tool.
Sure. Thanks.
Let me. I'm having some technical difficulty here. Okay, here we go. So, where's my tools? Here it is. Let me use blue color. You had written the problem AX equals B.
Yes.
And so this is let's call it the standard linear operation, the standard linear equation. But in this case, we would have something like what is it? Sine x 1 cosine x1 1 dot 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 1 sine of x. I'll just call it n cosine times a b c equals y1 y2 dot 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 yn. So this is the problem we're trying to solve. So I would here, rather than calling this guy y hat, I would build this matrix, call it A, and this matrix, this vector, rather than calling it, so this plays the role of the vector x in here, but I would rather call it something else, like, I don't know, just coef, for coefficients, because we can name the variables however we want.
I'll call it like matrix.
Yeah, and then do the backslash operator to find those coefficients.
Shift enter. Okay, that works. That makes sense. Because this is kind of our y hat, isn't it?
Not even.
Oh, not really.
Not really. Those are our coefficients, and our y hat would be our matrix times our coefficients, which is.
We ever use y hat, do we?
Left portion.
Yeah, this is our y hat over here, like our matrix times our coefficients. Yeah, that's our y hat.
So you could name it as another variable just to keep track of it, but yes, he's right. That's the y hat, and I think that should be fine for the first type.
Okay.
Oh, let me clear my portion too.
It's gonna be tough to test this one without the rest of these, I guess. Okay, but yeah, we'll say this works. As you were writing that, by the way, I kind of made a change here. This should not be 1. It should be like a column of ones that is x, like the size of x. Let's say like this is like a 5 element. So this is 5 by 1, 1, 1, 1, 1, 1. It should be the same size as like the rest of these over here. This is going to be like you'll have like sine of x1 dot 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 sine of x5 dot 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 like that. And it has to be the same size for all of those to match up.
There's a question, do you not need to multiply the matrix by the coefficients? Yes, you do. That is your prediction, your y hat, and it's done in line 13 right there. Not explicitly as an independent variable. We could name it y hat equals all that.
Yeah, like this. Minus y is y hat. There we go. Like such. But that's, yeah, they just did it in one line. I think the way they name things is a little bit confusing. But yeah, that's type 1. I guess type 2 and type 3 we can leave to your devices. Good questions, everyone. All right. Are we done here? I think I've given as many hints as I'm comfortable giving, unless people have further questions about that.
I think this should leave you all very well prepared to address the rest of the lab. So maybe we could use this time for questions.
Yeah. And while I'm doing that, I'm going to tidy the skeleton code just so that I can reuse this for my next lab. Let me stop the recording, actually. I think we're done with that part.